kicked off. So very happy to have Armin speak to us about Atlas. I first heard about this project from the PI when I was on an observing run at Keck many years ago. And he described it like this: I'm going to buy a 0.5 meter telescope, I'm going to put a really large CCD camera on it, and I want to observe from Mauna Loa, which occasionally has volcanic activity, so I'm going to put it on the back of a pickup truck. And now, if you're dealing with anybody else in astronomy, you would just look at them and say, and you hired where, and how long are you in this? But John Tonry is a pretty sharp guy, pretty crazy Phi Sigma guy too, and they came up with the project. I said, John, sounds good. I like everything except the name, because the high energy physicists have already sort of cornered the market on Atlas. And he said, I know, but I can't think of anything better, and it does make great sense. So Armin, please tell us about Atlas.
Yeah, thank you. Thanks for inviting me. It's always a pleasure to come back to Berkeley. I have many collaborators here and friends, and yeah, it's always nice to catch up and come up with new projects. So yeah, my talk today is about mainly about Atlas, but also about transients. For full disclosure, I'm not an asteroid guy. I'm a transient guy. I do supernovae. And so I joined this project with, we were just like a small group of 4 or 5 people when we submitted the proposal to NASA. And yeah, so the main goal is to find these asteroids, and I will tell you about that. But of course, you can piggyback and find lots of transients. And I will also talk about that. So just like a very brief history of CCDs and wide field time domain astronomy, since we don't have, well, we have many non-astronomers here. The advent of CCDs truly revolutionized astronomy. So in the beginning of the 90s, there were the first CCDs, very small, that were put on the telescopes. And so now finally you could get immediately digitized images. And that's actually how I got into astronomy. I was an exchange student in Portland State University in Oregon, and my master thesis was about CCDs. And for my thesis, I wanted to have a couple of pretty pictures, and I put it on one of these LX200s, and I was like, wow, this is actually really fun. And I went to the University of Washington, met my, later on advisor. We hit it off, and that's how I switched from physics to astronomy. And so I did my grad student, I was a graduate student in the beginning of 2000. And so I just like hit the wave of these new surveys that use these CCDs to find all of these things. So, so the first CCDs, they were like really small. You had like this 0.02 square degree areas. You could just like look at, a few objects. And then when I started to do my project in the 2000s, there were already bigger ones there. There was a Mosaic 2 at CTIO and Kitt Peak, were like 8 CCDs. And we were like, wow, this is actually really big at that time. It was 0.3 square degrees. And then in the recent years, it really exploded to, 7 square degrees pan-stars or DECAM 3 square degree, to the newer ones going up to tens of square degree. So within the last 15, 20 years, we really increased by 2 magnitudes our focal planes. And that really has helped us to do a lot of the science. It also has made it much more challenging. As Dave said yesterday, 15 years ago, there was no money for software engineering for the projects. And of course, SDSS was kind of like the pioneer of this whole thing. And now, without any good software engineering, you just don't have any chance anymore. So we went from like, I remember for the Essence project, we brought down a computer with a 0.5 terabyte. And that was like our huge computer for our image reduction. And now we have petabytes of data. So it really has changed in the last 10 to 15 years. And it transformed in a very data-intensive industry, basically. So one thing that got clearer and clearer, that size alone is not the only important thing. So normally you would think, hey, you have a smaller telescope, you just make it bigger and bigger and bigger, and that's what matters. However, it's also as important how big the focal plane is. If you just are interested in spectroscopy of a single object, then a bigger telescope is much better. But for surveys, it's as important to have a really big focal plane. Because if you have a big telescope and you have only a small field of view, you're as good with a smaller telescope and a much bigger field of view. And so this is captured in the étendue, which is the area of the telescope times the focal plane. And so if you look at these, this is relatively like 5 years old, so we don't have a PDF yet on it. But here, are the different surveys. You have the telescope diameter, and you have the focal plane. And you can see, it goes from relatively small all the way up to 8, 9, 10 square degrees. And then you can calculate this survey power, and you can see that, for example, Pan-STARRS has a relatively high étendue, similar to DECAM. Even DECAM is a much bigger telescope. So, as I said, we have now, we are in this area of this wide field time domain surveys, and what you do is you normally combine two things. You combine the time domain, you look for solar system, for variable stars and transients, and when you stack all of these images, you look for the static sky, and you can look at our galaxy, do archaeology in our galaxy, or you can look into the high C universe. So, I will talk a little bit about Atlas, some of the asteroids and near-Earth objects that we look at, and then I will go a little bit into this discovery space. There are different ways how you can make a discovery. You can have dumb luck and grab this opportunity, and that's what I did. I think probably I'm here because I was at the right time, at the right place, and then I actually said wow, this is really cool, and I ran with it. And that was one lesson I learned. And then you can also do where there is a discovery and you hunt for it. And I will talk about that with a kilonova. And then you can also leech on existing resources. You can call it repurposing of resources to also do discoveries. So this is a meteor crater or barrier crater in Arizona. And about 50,000 years ago, a meteor hit. And you can see, I think it's like 200 meters deep. It's a huge boom. If you were anywhere around there in North America, you got pretty much, you were in dire straits. So this was not like a global thing, but definitely locally it was no fun. Then, of course, more recently, there was like a 50-meter metal, iron, nickel meteor. That makes a big difference. Of course, if you have a very dense object and you have basically a 50-meter bullet hitting Earth, you get something like that. If you have kind of like a 50-meter loose rubble thing, or with like water and ice in it, could be a comet or it could be a loose asteroid, then you have something like that where it explodes in the atmosphere. So this one destroyed 80 million trees in 2,000 square kilometers. You have to think about it. It was, I think, 50 times stronger than Hiroshima. That was like a big thing. There was no fatalities, and the only reason was it was in Siberia. And as we know, not so many. The density of people in Siberia is not that high. So that was just luck. Of course, you have oceans that can always explode over oceans or non-inhabited areas. But if this thing hits anywhere close the US, it will be a lot of fatalities depending on where it hits. And then, of course, you have the KT impact that is believed to have extinct the dinosaur. And so it's a big thing. It's like 170 kilometers in diameter. It's here in the Yucatan Peninsula. And I think it's not completely established, but there's very good evidence that this at least had a major role in that extinction event. And I still remember that. That was before I was in astronomy. And I was like, wow, this is like absolutely amazing. So they predicted that this comet is hitting Troubadour. And of course, lots of telescopes were pointed towards Troubadour, and indeed, it got disrupted before in several pieces, and then you had like this string of comet pieces hitting Troubadour. And I think the Earth probably fits or close to fit in one of these explosion areas. So that was also a huge event. So over the years, a lot of, it got more and more attention. And then in '98, of course, we had like 2 movies addressing that. And so the first one is Armageddon. And, of course, story, you have this asteroid or meteor, and it's hitting Earth. And what do? You have to drill a hole in it and detonate an atomic bomb. Of course. So instead of like having an astronaut trained to drill a hole, they of course use a driller and put them into space, because otherwise it would be really easy. And who do you ask? Bruce Willis, of course. I mean, you have to have a real man to do that. And someone like Bruce Willis needs to have the right equipment. So you have a near zero G object, and you have 800 turbo horses in there. So basically, if you start this thing and you hit a bump of that size, you're lifting off and you're gone, But then this asteroid was depicted as like having this needle-sharp rocks. When you're bombarded all the time with space dust, you don't have needle-sharp rocks, You look like the moon with like craters and lots of dust and stuff. But last but not least, only a good guy can stop a bad guy. They had to have these guns on these rovers when they were sent to space. I mean, it's like, of course. So, I don't know, I mean, pretty much every single stereotype they could come up with, they put in this movie. Yes?
There was a Simpsons episode that was just as realistic.
Oh, yes, that is probably true.
In its own way.
And every stereotype and everything they could do wrong scientifically, they did wrong. Yeah. So Deep Impact was the other one, and that was actually much more sound scientifically. And of course, you have the monster wave. I mean, it would be rather catastrophic tsunamis if something like that would happen. And so the attention to these things, to this possibility of these events was really growing in the last few decades. Then, of course, when you have one asteroid fly by at the distance of the moon, it gets all hyped up in the press. But, I think this is just like what we have to deal with. We have to, sell what we are doing, and it gives us a funding. Then the real game changer was Chelyabinsk in Russia about 5 years ago.
Video of that asteroid in Russia, barreling toward Earth at 40,000 miles an hour. It exploded into pieces 19 miles above and 25 miles south of the city of Chelyabinsk. People thought it had missed them entirely until minutes later when the shockwave arrived. Shattering glass, crushing doors, and knocking some people right off their feet. More than 1,000 were injured.
How much warning did people in Chelyabinsk have?
None.
Yeah, so that was just at the time when we actually built our system, when we built Atlas. So that was definitely also a boost for us. And so that was our idea right from the beginning, to have an early alert system that if you have some of the smaller ones, you can at least give a couple of days or at least a day warning. And if you have some of these bigger ones, that it goes, the warning from 1 week to, for the real big ones, like months or years. So here's kind of like, I was really impressed by it because it kind of like gives you a scale. So you have this nearly 300,000 objects that are at the size of Tunguska and Chelyabinsk. And these are a lot. And we only know about 1% of these. It's really a small number. So here is a KT event. it's very unlikely we miss one of these really big ones. We normally know it. I mean, it's a very small chance that one of them really slips through and would hit us without knowing. But these ones here, if you think about Tunguska, something higher than that, and there's a good 30, we only know 30%. So there's a lot of room for improvement and a lot of work that we still have to do. And so the 1992 Space Guard Survey report said, like, okay, we want to have 90% of the NEAs that are up to 1 kilometer, and that's basically where we are right now, and I think we're actually now above that in the recent decade. Yes?
You're showing a distribution here by number. Is it flat with mass, or how do you think of this?
I don't know if it's flat with mass. I don't know.
Energy, perhaps you could quantify it by energy.
Yeah, I mean, of course you have the usual distribution where you have much more small ones than the big ones, but I don't know the number of in mass. But it probably is like that, As I said, I'm not an asteroid scientist, So there have been asteroid surveys since I started grad school, end of the 90s, beginning of 2000. There are linear. I was a little bit involved in Lonius, Space Watch, and then there's a more modern service like Pan-STARRS that I also was a part of, Carolina Sky Survey, and NEORISE. And so if you look at the distribution of the number of discovered near-Earth asteroids, it really has gotten dominated by Catalina and by Pan-STARRS, and now recently by Atlas. So that was kind of like, we started about 2016, 15, 16, and we are now one of the biggest producers of these near-Earth asteroids. So it was a project funded by NASA to find these asteroids. The PI is John Tondry. He is, as Peter said, a very energetic guy with lots of great ideas. And he really pulled it off, So the unit cost for one of these units is between $500,000 and $1 million. And we're trying now, we have 2 that are working, and we're trying now to get a couple more on the ground, especially also in the southern hemisphere, yes.
So you'll talk about what it means to find and not lose?
Yes. So what you need to do is you need to have at least 4 detection to get the orbit. So we have, like in Pan-STARRS and lots of the other surveys, when you have only 1 or 2 detections in some of the part of the surveys, like for the transients, you lose them. If you have only 2 detection, the uncertainty in your orbit is just too high, and even though you can send it to the MPC, it doesn't really help you. You need to have about 4 detections spaced, preferably over a couple of hours. And the issue is also that lots of times you have chip gaps, you have bad columns in your detectors. And one of the mistakes we did in Pan-STARRS at the beginning, we only had 3 or 4 epochs, and we had a lot of chip gaps and bad columns. So normally you lost at least 1 detection. And so our efficiency was worse having 4 images than having then later on 5 images or more. You have a smaller area, but you just are so much more efficient, you don't lose most of them. And so we had to change a little bit our service strategy for Pan-STARRS.
So as you accumulate a catalog, is there a commitment to do re-observation on that catalog in the future?
No, there are too many. It's like if you find a special object, then it's different. Like this interstellar object that Pan-STARRS found that passed through, of course, you throw all the resources you have on something like that. Or if you would find something that comes towards Earth, then of course you also trigger follow-up resources and say like, hey, send out an alert, please confirm that this object right now with the error bars, it could potentially hit the Earth. So you do that. For everything else, you just kind of like, if it's a new one, then you get registered as a discoverer of that object. and otherwise you just like add it to the database, and it normally gets linked back to the previous detections. And of course, as more detections you have, as better is your orbit. So lots of them, they are in a stable orbit, and the only way they could get dangerous is if they pass Jupiter or they get disturbed by Jupiter or by some of the other objects, and then they get kicked out of their orbit, and then suddenly they are in an orbit that gets you near to Earth. So right now, no object is known that is predicted to hit us. But it's really good to observe all of these objects and keep track of them, because sometimes a small change in orbit on the long run could get it onto an orbit that hits us. And the sooner we know it, the better. You don't want to do a Bruce Willis and explode it right before it hits Earth, because all these fragments, when they hit the atmosphere, that still has a huge damaging effect. Probably nearly the same than if it hits you in one piece. It still deposits all this energy in the atmosphere. What you really want to do is, years before, you want to send something there and just like give it a little kick. And that little kick over a couple of years in orbit will deviate it enough that it misses the Earth. So that's kind of like, for the big objects, that's what you want to do. You want to get it as early as possible to be able to change it. And for the smaller ones that you don't have in time, you want to at least know where it will hit. Even if it hits in the ocean, the tsunami it will create, even if it's a relatively small one, can also be devastating. So that's kind of like the goal in this whole game. And so we go and observe the visible sky, which is about 3 pi, every other day, maybe a little bit longer. It just like depends how the weather is. So if we have good weather, we just get all of the observable sky pretty much all the way down where the telescope can go every other day. And we use these broad filters, which is a combination of G and R and R plus I. So we go as broad as possible to get as deep as possible, but we still conserve some color information. So we have information about variable stars or stars and other things in the galaxy. So here's the impactor size, and that's the fraction found. And so Tunguska is here, Chelyabinsk is here. The discovery probability, of course, depends on the size and the survey duration. So if you lose a few days for weather, that of course you create a blind spot. The size really has a big impact on how bright the object is. The small objects, 10 meters, 20, 30 meters, you just cannot see with a small telescope like that, like weeks before. And of course, having a big telescope do that is just like too expensive. And so the large ones, the kind of like civilization killers, we normally see them years before they would impact. So by continue to monitor, we should be able to identify them in time. So
how did you compute that probability? Is that based on a simulation?
I think it's a combination. We added fake stars to the images. Then you also look at known objects, how soon you find them when they're coming, and you put all of these things together, and you can kind of like get this probability. You don't want to do it either or. I mean, you want to anchor your simulations with some of the empirical evidence, and then you're reasonably confident. Yeah. And so here's, again, both simulations and real data were for 50 meter and 140 meter. This is like the warning time in days. So you can see like 50 meters, normally we should get it 5 days before impact. But of course it goes also all the way to 1 or 2 days, and you do miss some. Especially the ones from the sun. The sun is your big blind spot. So that's like this cone of like 30, 40 degrees, and you just don't have any chance getting anything that's coming from the sun. So we are now working. We have both working on both summits. We have been pretty successful. We do have about 0.25 terabyte per night. This is nothing compared to the real atlas of the particle physics. Yes.
Which two summits? Mauna Kea, Mauna Loa?
It's Haleakale and Mauna Loa. Yeah, and so we're trying to put one into Flagstaff, and we're also trying to get one in the southern hemisphere. We would get some money from NASA. Basically the construction cost would be covered. We need the commitment from the site to then do all the facilities and things like that. Yeah, so the nice thing is with Atlas, it has a relatively big full width half maximum. It has basically, nearly, it has 2 arcsecond pixels. Pan-STARRS has 0.25 arcsecond pixels, so that's nearly a factor of 10. And that's the reason if you compare, this is kind of like the Pan-STARRS field of view, this is the Atlas field of view, this is just one chip, 10K by 10K. These ones here are, I think, close to 100 chips. And so the volume, the data volume of the smaller field of view is much bigger than this one. What you lose is resolution. With this Pan-STARRS, we have like 1 arcsecond seeing. With Atlas, we have 2 arcsecond pixels, 2.5 arcsecond full width half maximum. So we are completely undersampled, which does kill some of the science, or we just don't go as deep enough if you would have higher resolution. But you get this huge field of view that would be much more difficult to get with these better resolution. And it also helps you with the data volume. We have much less data volume effectively than we have with Pan-STARRS, which really helps a lot as well. So, different systems are good for different things. You will not do any high redshift galaxy science with Atlas. You use DECAM or Pan-STARRS or HyperSupremeCam. And but for this it's really good, and we're finding also a lot of transients in the near universe, like low redshift ones. So here's a comparison again between Pan-STARRS and Atlas. So Atlas is just like doing the whole thing that is visible, besides the part that is covered by the sun. Whereas Atlas in a given night is just like doing this more pencil beam surveys. So we are finally starting, everything is running well. We have the whole asteroid stuff under control now. This is going really well. We have been one of the most prolific discoverer of supernova in the last 1 or 2 years. Assassin is another one, and PDF, I think, and Pan-STARRS are like the big 4 right now in that game. We have discovered 130 NEOs, so every other night we probably find a new one. In a given night, about 15 known ones, so you keep track of all of these near-Earth asteroids. And we have now this catalog of about 200 million stars, and each of these stars has about 200 detections per year per object as a median. Some of them have 400, some of them have less, but I mean that's a really nice photometric catalog down to a depth of about 20. So I have just gotten this variable catalog at SDSCI. I'm vetting it right now to make sure everything is okay. And the goal is agreement between John Tondry and us is that we will make it public in as soon as possible, probably in a few months. I mean we do want to vet it. If anyone is interested, want to have a look, and just like it's always good to have real scientists look at it.
Yes.
Yes. Yeah. Absolutely.
Presumably, photometric calibration is not as high a priority for you as it is for, say, Pan-STARRS.
So the nice thing with Pan-STARRS is we have now this really nice photometric calibration all over the sky. And so what we're doing is we just use Pan-STARRS to make synthesized catalogs, and then use that. So actually, one of my projects at SDSCI, I just got money for that, to hire someone, and I hired someone, is to do the photometric transformation from Pan-STARRS to all of these other big like most common telescopes, STECAM, everything, you know. And then make a database that has just stellar objects that are well vetted for photometric calibrations in all these different synthetic passbands. So if you have STECAM images and you want to have a quick calibration, you just go there, grab the stars, star galaxy separation has already been done, the transformation has been done, it will be published in a paper, and then you can just go with that. And this will be probably a better photometric calibration than you can get with going to standard stars. So that's also one thing that in the next few months I wanna get out.
How near is near? How near is near, or what's near?
A near-Earth object.
Oh, I don't know what the definition is. I think the definition is that it crosses the orbit at a certain distance. And most of them are never really getting, you know, if there's not a real disturbance of their orbit, they will always whiz by. I mean, it's a small target. You know, if you think about the Earth, it's not very big if you consider how big the solar system is. And then you have these, you know, 200,000 or 300,000 objects. It's actually very sparse.
Usually people don't start freaking out until it's like 10 lunar distances away or something like that.
Yeah, I mean, anything that is not closer than the moon, you know, I mean, and even then, it's still, there's a lot of space between the moon and Earth. So, I mean, it really gets hyped up. You know, of course, you have like this asteroid, and you know it will miss us to 99.9999%, and you're just not 100% sure. And then the press is doing something, and then it dies down because it just like whizzes by at a big distance. But you know, on the other side, we do want to keep track of these things. It will happen at some point. That sounds really does again. Okay, the unexpected. So this will be not about Atlas data. This is like a different survey I was involved with. It was a microlensing survey towards the LMC with a mosaic camera on CTIO. And so we were looking for this microlensing where you have, you know, a background star, you have some kind of dark object in front, it bends the light, and you see this short brightening of the star caused by this dark object. So that's one way to find potentially dark matter if it is in these compact objects. And so I did this survey. That was kind of like my thesis project, and then I did it also for in the first years of my postdoc. And there was this one area where we just got a huge amount of alerts, 10 times more than in any other field. And you know, you have to go through all of these alerts. It's really annoying. And I was working with another grad student and another postdoc, and you know, things were flying by, and I was like, yeah, man, I mean, this is really annoying. What is it? It looked strange. It looked like this blobby things. And then I got this email from this other grad student. And he was like, oh man, look at this. I popped up the whole image, and it looks like this. You know, and we were like, what is that? You know, you have these beautiful rings. These are like 3 amplifiers. So this is like several arc minutes on each side. So this is like these rings there. And, you know, we are just like, you know, beginning postdocs, graduating, I had no clue. And we were like, you know, discussing what it is, and was going back and forth. And then we sent it out to our collaboration. And they actually didn't know it first either. Until like half an hour later, someone said like, hey, isn't Supernova 1987A there? And aren't these the light echoes of Supernova 87A? And of course, I mean, these were the very rare light echoes that were discovered, you know, in 87, like, you know, 15 years ago. And we rediscovered it. So just like very quickly, what are these light echoes? These light echoes are just this scattered light of a dust filament. So you have Supernova 87A here, you have an observer here. They have a direct path, but then if it goes a different path, gets reflected here, it's a longer path length, and of course, it arrives later. And if you have an ellipse where both the Supernova 87A and the observer is in the focal plane, the path length from one focal point to the ellipse to the other focal point is the same. So that's the surface of equal arrival time. So when you have a dust sheet, you see the light, the scattered light, at the intersection, at a given time, at the intersection of this ellipse that corresponds to this time since the explosion. So that's the reason when you look at the sky, you see the cross-section between a dust sheet or filament and this ellipsoid, which is a ring. That's the reason you see these rings. And if you have these dust sheets at different distances, you have rings of different radii. And then a little bit later, your ellipsoid is a little bit bigger, so your rings are getting bigger. And if you look at 87A, at these light echoes, it's exactly what you have. You have these two rings. It means two different dust sheets in front of 87A. So that was kind of like this, was kind of like a cool thing. We rediscovered it, and then we put it away. And then, with time, we found these other things. And they just looked like 87A's light echoes. But they were at very different places, and they had a much lower apparent motion. And we're really, really busy with our survey, and so we put it into our attic where we put all objects we don't have time to really deal with, but we don't want to lose them. And after like 1 or 2 years, I went back and said like, okay, this is like, let's try to figure this out. And so when you have light echoes, you have these rings or arclets that move away. So if you want to know the source, you just extrapolate backwards. And that's what I did. So here's like the original image, a template image, and this is 5 years. So you can see after 5 years, it moved a few arc seconds. And so I just kind of like fitted these light echoes, calculated the orthogonal, and then extrapolated backwards. So these are like the difference images between later epochs and the previous epoch. So all static objects, all the stars are canceling out, are subtracted out, and what you're left is a difference flux. That's the reason you see as positive flux the later epoch, and as negative flux the previous epoch. And so I extrapolated this backwards and then overplotted it on the LMC. And I tell you, it was really like this discovery thing. You like start. So first thing, I didn't do it electronically. I just had a sheet, and I kind of like drew the arrows, and I was like, whoa, this is kind of like, I started with this one here, and so I got like this half circle. I was like, this gets exciting. And then I had a few from here. I was like, okay, now it doesn't make sense anymore. But it turns out that these are the light echoes of 3 objects. And so the next thing was, what is it? So I overplotted the novae in green, and there was like, there was one here and here, but it wasn't kind of like a full hit. And then when I overplotted the supernova remnants, it all made sense. These are the light echoes of these old 400 to 1,000-year-old supernovae. So what you can do is, you really see the light, the scattered light of these old events. So you take a spectrum, and you get the spectrum of this old supernovae. It's a true time machine. It's as if we have a telescope 500 years ago. And then you can compare these spectra, and I subtracted the continuum. You can compare it to your templates of a supernova that you know of, and you can even identify the subtype of supernova it was. So that was an overluminous type 1a supernova. So that was really cool. So we're like, hey, if we can do it in the LMC, we can also do it in our galaxy. And so I went and looked for the light echoes of Cas-A and Tycho, and indeed we found them here. So here you see again this vector plot. If you average all of this vector for a given group, it's here. So Tycho is here, Cas-A is here. It was just like perfect. And I ran with that. That was really a lot of fun. And so we got spectra, Krause et al. Followed it up, our light echo, and we did the same we did with a supernova in the LMC. And since then, this has been a huge amount of fun. Light echoes are the only thing where you can look at the same astronomical object from different directions. And so we did a study of the symmetry in Cas-A. We have now a spectroscopic time series of Tycho and Eta Carinae of the great eruption. And we can also now get the distances. So this whole thing, I have a whole lot of talking about all the science that you can do with this one.
principle, you can also reconstruct the 3D distribution of the dust.
Yes, yes. But who cares about the dust?
They're part of the instruments.
Yes, that's true. It's part of the instrument.
That's right.
It's actually true. I mean,
You
so
could fully calibrate it. You might find that there's other sources in there. Because you could eventually build a full calibration of the dust in the...
you can get the thickness of the dust. That's one of the side parameters you have to fit when you do this. And actually to really accurately. And I found that the thickness in the LMC is significantly higher than the one in our galaxy. But yeah, it's just like too much
Yeah, there's too much.
things to do. Okay, changing gear a little bit. The hunt. So we have seen, everybody knows about the cavitational waves. It was just like absolutely awesome. I don't have time to show the movie. We have LIGO and Virgo. We found the first gravitational waves about 2 years ago. It was really a beginning of a new era. And you know, if you look at the signal, nobody expected to see such a huge signal with the first event. The second event, if you look at the same plot, it just looks like noise. I promise, you know. But we got really lucky, and there was like this really, you know, high signal noise event, and everybody was like absolutely astonished. Of course, you don't expect electromagnetic counterpart for a binary black hole, or only a very weak one. So the holy grail, in a way, is to find this electromagnetic counterpart for a kilonova. And so here's just like a very quick little movie. So you have these two neutron stars. They're spiraling in. They start to disrupt each other tidally. They form this disk of debris. And then at the end, they produce a gamma ray burst. So that was kind of like the model. And everybody was like, so you know there could be something to discover. And it's not like the unexpected, where you just stumble upon it, like me. But it's like, hey, you try to get this and discover it. And so the idea was that, oh, we will not find one until LIGO finds things to about 200 megaparsecs, 150, 200. Then the expectation was really faint, and you can only do it with this big telescope. If you find something that is closer than 50 megaparsec, that's like where it's really getting interesting, because then they are so bright they can do it with the small telescopes. And in early August, just 2 weeks before it was discovered, there was this conference about kilonova, and they had a wager. They asked, when do you think will be the discovery year of kilonova? 2017, 0, like really 0. 2018, one single one. Everybody thought it's 2019 or later. And yeah, so that was like, you know, everybody was like, yeah, we still have time to get everything set up. Then the first thing happened in mid of August. Virgo started to really work. That's the third detector. And with 3 detectors, we have a much better localization. So they found this binary black hole where they had this first signal by Virgo. And that changed the area from 1,000 square degree to 60 square degree. So 2 things were important here. Virgo worked. So they knew it actually, look, we got a relatively low signal noise, but it actually worked. And that was 2 weeks before the end of that run of this year. So everybody was like, wow, that's our last great target, and you know, now we have to wait a year. And then 3 days later, this happened, and it was just absolutely amazing. So gamma ray, there's a gamma ray detected by Fermi. And 6 minutes later, there was a single detector binary Newton star signal detected in, I think it was in Hanford. In Livingston, they had a glitch. So I don't have a thing, but you have this really strong electric signal here, and so it was flagged as not reliable. So it was only a single detector detection of this binary Newton star. So now imagine you are at the detector. You get a single detector alert. You know at the same time there was a gamma ray burst. They have never before sent out an alert with a single detector. It was always like, hey, you need 2 simultaneous detection with both one, and then you can be sure. And I have to say, it took some guts. Half an hour after they found it, they sent it out. And was like, screw it, it's only one detector. In the other detector, it looks like there was a glitch, but it looks like it's there. This is real, and we sent it out. And it was clear when they sent this out, all hell will break loose, you know. So this is what happened. So they sent it out, and these are like some of my collaborators. So it's Dave, he's a grad student, and his advisor. And so Ryan was in Copenhagen at a workshop, and he actually took the afternoon off with his girlfriend doing some sightseeing, and then he gets this text, you know, drop everything, check your email. And so that sounds like a joke, by the way, why it was. You know, he was like, okay, you know, are you, and I wouldn't put it past Dave to have a joke like that, to actually, you know, get him away. And he said, like, I might leave, but if you're joking, don't tell me now, I will not be amused. That's like your advisor saying that. And he was just like, I'm not joking, Jesus, man, you know, this is like real. And this really, I mean, things like that happened all, I mean, we had like, I think there were like 50 follow-up groups or something like that. So it got, you know, at the beginning, it takes a while for them to get these localization maps all correct. And that localization map actually was jumping around depending on what time. And it was not insignificant. And so Ryan and Dave and Charlie, they actually picked the right map and started to follow up. And so you had two hours time before the field was setting. So that was like, you know, we were just barely able to do this. So they went, and at this time, they started observing. So they didn't have templates for these fields from the same telescope. So they got it from Deccan. And then Charlie looked at them, blinked them by eye, and said like, hey, I found something. So this is like the archive image, and then this one is a discovery image. And look at this bright object here. It was so bright. I think if before anyone would have said like that first kilonova will be bright like that, you would have been laughed out of the conference. So about 25 minutes after the image was taken, they discovered it. They immediately triggered Magellan time. That was like a half an hour later, they took the first spectrum. And then soon later, they were putting out the GZN. And there's like a lot of stories about that too. It got very political and ugly. But they were extremely fast. I mean, it really is like amazing. And that's the reason we have these two spectra right after one day. Otherwise, if they would have not turned around within 1 hour, it would have been absolutely impossible to get a spectra. And it was really crucial. So that triggered a whole massive follow-up. There were several other groups that independently discovered it at the same time, or like a little bit later. But it was just like absolutely amazing with how many telescopes there was a follow-up after one. And you know, I think you've probably seen, and we have had a couple of talks about it. I don't want to go into science. It is just like absolutely amazing. It was the best or like the most important astronomical discovery in like a decade or something like that. So repurposing the instrument, I will just do it like for 5 minutes very quickly. I'm sure you have also heard about the Kepler Telescope, awesome telescope with a purpose to find exoplanets. We have heard about it also yesterday. And so some colleagues of mine, they had the idea, hey, if you would get a supernova light curve with this instrument, it would be awesome. The problem is you have to read out, you have to designate which galaxies to follow. They got accepted, they followed up 100 galaxies, and they found nothing. And a year later, I gave a talk in the University of Maryland, and after my talk, this guy comes up, this professor, and said like, hey, do you want to see something cool? And I said like, sure. So he plops up his laptop and shows me that. And I was like, you know, I started drooling, you know, I was like, holy matoli, you know, how did you get this? So they were a group looking for AGN activity, and they had 400 galaxies. And it was just small number statistics. Brad and Peter, they had 100 galaxies, they were expecting 1 or 2, they didn't find any. they were looking for AGN activity, and we actually found 6 supernova in this 400. So the other group just got really unlucky. So I put all of these groups together. We started to collaborate. And so what you want to do is with this light curve, when you have, for example, type 1a supernovae, you have this white dwarf that explodes. If this binary companion is a star, then you will see this excess light at the beginning of the light curve. So that's illustrated here. So you have a white dwarf exploding, and then it hits this companion star, and you see this shock. So what you see is, instead of like the normal light curve of a type 1a, in these very first days, you see this excess flux. And Dan Kaysen here has done a lot of modeling with that, and we're collaborating. And so we found 3 type 1a supernovae in the first Kepler mission, and it's amazing, look how smooth the light curve is. We just don't see any signature like that. And so you have these 2 models, these 2 white dwarfs merging, and you don't see any excess flux at the beginning, or you have a white dwarf and red giant or main sequence stars, and you would see something like that. So this is one of the best ways to get constraints on what fraction of type 1a supernova are produced by which channel. You also can do other things. So these are the light curves, the early rise time of 2 type 2p supernovae. And when you compare 2 models, you can see here an excess flux. It's just like rises so fast that you normally cannot explain it with a typical model for type 2p's. So it looks like that there was some material, some shell that got hit and gave a little bump of excess energy into the explosion. And then here, when you look really closely, you can see also a little bump that could be a shock breakout. If you look closely and do this analysis, it actually is significant. I was very skeptical at the beginning too. And when you look closely, it is actually a significant detection. Then the gyro died one of the gyro died, had only 2 left. So what they did was, they used the pressure from the sunlight as a 3rd gyro. And that's how they could expand their mission to K2. And the problem is, you can only look in 2 directions, forward and backward. When you look forward, the Earth is in the field of view, so they don't like that, so you look backward. But then the field that gets observed, you can only see in twilight on Earth. We only get the Kepler data after 3 months. So you want to detect this supernova in time to get a spectra. And so we have been fighting for all K2 to find these objects in twilight and still get a spectra. And this here is the first one that we got. It was a type 1a. And we got it with Gemini at 2.5 air masses and -14° twilight. I mean, it was really, we were like sitting there, and I was like, look, it's really bright. It was 0.03, and it was like, honking. And I told Steve, who is on Gemini, just talk with the operator. I know it's 2.5 air mass. I'm not supposed to go all the way down, and but just push it 5 minutes, and we will have the spectra, and we got it. And you also can find some of these exotic things. That's the last thing. So in our guy who does a reduction of the light curves, we get some new data after 3 months, and he's like, hey, here's a new supernova. He sends out this plot. And I look at that and was like, it's a type 1a. Just looks like it. And then you look at the time axis, and this is 2.2 days. You don't have supernova with a rise time of 2.2 days normally. I mean, it's typical type 1a supernova is 17 or 18 or 19 days. And so this is one of these really fast transient. We got it in 1 epoch with DECAM. And just because we only got it in 1 epoch, we didn't trigger on it, we didn't get a spectrum. That was really unfortunate. So next time, so that was why that peak. So next time we had time that was not vetted out, was 14 days later, and we just missed it. So this is just like a paper that just got accepted. That should come out in a month or something like that, and you can compare it to all of these other supernovae. So just summarizing, we are now in this era of optical wide field surveys. Yes?
Do you guys have any theories of what type of transient it is?
Yeah, we do. So it's probably a type 1b. So it's like a very compact star that explodes, and it must have gone through some mass loss a year before or something like that. And so it has this shell. So if we don't see it first, it explodes and then runs into this shell, this dense shell. And then we basically see when it breaks through this shell that it goes up like that. And it's actually as bright as a Type 1a supernovae. So actually a little bit brighter. So it is very bright, and you cannot explain it with radioactive decay. And there's this whole group of fast transient, with pan-stars we had like a group, Maria Trout did that, and PDF found one or two, and superluminous SNLS. And so this is kind of like the idea. Now with a beautiful light curve, we can get excellent models that fit really well this data with this shell. And so David Katami has done that with Dan Kaysen here. We're collaborating on that. And so you can really constrain now the parameters of this shell as well as the explosion.
But on this curve, what's the that's not an exponential decay?
No, it's not.
Are there multiple phenomena? What's the story behind that sort of?
So I think what you have is you have a supernovae that is very relatively faint. That is probably, that went off here and was like this. And all of that stuff is the supernova going through the shell, shooting up, and then passing through, and then it drops again.
So that's consistent with a previous.
Yes. So actually, I should have shown we have now the figure where we show the model, and the model just fits nearly perfectly. You know, it's really an excellent fit.
Can you see those previous events? There's no cataloging of that would show that
Previous mass ejection, would it leave a signature?
No, I think it's too faint. It's the previous one. You know, I mean, it's like something like at a car with a great eruption. So you're like all the way down, you know, at -14, -15 absolute magnitude, so few magnitudes, 4 or 5 magnitudes below, and you know, yeah, the service didn't go deep enough. I mean, we looked up, and there was no other transient there before, unfortunately. It would have been really nice, yeah. Yeah, so I just, you know, hope you enjoyed talking about Atlas. I think NAO servers are really important. We can map the solar systems. We have an early warning system now in place with Atlas and several other surveys. We have Bruce Willis on speed dial. If something happens, that we can do something about it. And my research interests are mainly with the transients that we do discover at the same time with these wide field surveys. Thank you.
Time for a couple questions.
Just thinking about real-time decision-making in the context of Kepler. So Kepler plans out all of its targets because the downlink is not enough to actually load up,
Yes.
bring the data down, so all these little postage stamps select,
Yes.
and that's all planned in advance. Is there any capability for doing like on satellite decision-making about how you might pick a field or downlink data?
So with Kepler, no. But here's the thing, that's actually a really good question. With TESS, it's a follow-up mission, which is actually 10 times smaller telescope, but they have 2,500 square degrees of a field of view that they read out completely. And so we don't have the Kepler thing where you have to designate what you read out. You have the full image every 30 minutes. If we would have known that a few years ago when they were still planning that, we could have asked them to actually save the 2-minute data. It gets saved in a buffer. And so you could have triggered you find a supernova from the ground. If it's buffered for more than 1 week, you could have go back and say like, hey, at this stamp, don't throw away, it's a 2-minute data. It's a really bright supernova. We get a 2-minute cadence light curve, and we could have gotten it. I mean, it was one of the ideas we had at the workshop, and technically it would have been possible. With space missions, doing any significant change late before launch is not going to happen. And so we talked with them, it was just too late. But yes, that would have been a really cool project to do.
So I have a question that follows up on that based upon David's talk yesterday, which is the survey design. What type of galaxies did you pick, and what thought went into the list?
Yeah, so we were pretty successful at the beginning, and that's the reason they were getting more and more open to have bigger and bigger galaxy lists. At the beginning, K2, we had like 2,000 galaxies. Now C16 and C17, we have between 10 and 15,000 galaxies. So we kind of like merge different information. We go to net, get all the known redshift galaxies. And so that's our primary list. This is how we start. We get everything below 0.1. And then we go to pan-stars, get all the photometry from there, and then we start to fill up based on, and we just do it then by magnitude. Because we say like, you know, as more light there is, as normally it's a higher chance of a supernovae. So this is not completely unbiased
So
by
you're
far.
trying to maximize by the total number of supernovae?
Yes.
Okay.
So we have not done it with, that we have it unbiased. However, with TESS, we don't have this issue. TESS is so much brighter that we should be able to find all supernovae with Atlas and PDF, CTF and Assassin. And so there we should have a much more complete sample, an unbiased sample, than we have with Kepler. So with Kepler we just got the, you know, the low-hanging fruit, and now with TESS we can do the more statistically sound analysis.
Other questions?
So for in the NEO situation, is there any advantage to consider satellite observation at Lagrangian to cover that sun black cone? And
I think
if
that's
so,
a-
are there data rate issues there where you might want to do something?
Yeah, it's a cost-benefit analysis. It's really expensive to put a satellite or to put something in L2. And so, is it worth the billions or lots of hundreds of millions to put something there just for the smaller ones that are getting hidden by the sun? Or you just like say like, well, if it really comes from the sun and it's like 20 and it wipes out a city, that's just like really, really bad luck. So I'm open for putting it there. I would support it, but I doubt Congress will go for that. It's too small a chance.
NASA's definitely invested the most, but it's typically $1 million scale stuff they're investing in, right? Is that fair to say?
Yeah.
NASA's definitely invested the most in NEO science,
Yes.
but it's definitely on this scale of Atlas.
It's on this scale because you can really do a really good job with this, you know, a few million, $10 million things, and yeah, it's you know.
All right, let's thank Armin again. Thank you.